Université and Marie Curie, who is going to talk about from the critical Ising model to spanning tree.
Okay, so first of all, I would like to thank the organizers for the invitation. So this talk will consist, first I will define the Ising model and spanning trees, and then define their critical versions, and then state the results proving a relation between the two, and then proving this result. So the Ising model, you've maybe seen the definition already, but it's defined on a graph G, which will suppose to be finite. So here is an example of the honeycomb lattice. And on this graph, you put spin configurations, which consist of plus or minus ones. So they're drawn with different colors, blue and green. And so we're interested in the set of all spin configuration that is in -1, 1 to the v. And then it's a probabilistic model, so you put coupling constants on the edges, that is weight, positive weight on the edges. Every edge E has a weight J of E. And with these weights, you define a probability measure, which is called the Ising-Boltzmann measure, which is as follows. So the probability of occurrence of a spin configuration is proportional to exponential, the sum of all edges in the graph, of the coupling constant times the spin at x times the spin at y. And then there's a normalizing constant known as the partition function. So it's simply the sum of all spin configuration of the weights of the different configurations. So this is the Ising model in general. So we'll be interested in the Ising model defined on isoradial graphs, which are a specific family of graphs. So now I will define what an isoradial graph is. So a graph is isoradial if it is planar and if it can be embedded in the plane in such a way that all faces are inscribed in a circle of radius 1. And also you ask that the circumcenters are in the interior of the faces. So probably isoradial graphs were first introduced by Duffin when he wanted to study discrete holomorphic functions on graphs. And then it's been put to very beautiful use by Mercat in 2000. And the definition as stated here is given by, in a paper by Kenyon. So all the regular lattices are isoradial. So here is the example of the honeycomb lattice. And so you can draw all the circumcircles around the faces, and they all have the same radius. The square lattice is also isoradial, and so here are the circumcircles. The triangular lattice is also isoradial, but you can also think of a more general example like this one, and then if you draw the circumcircles, they all have the same radius. So a full characterization of isoradial graphs has been given by Kenyon and Schlenker, so we kind of understand well how they are. Okay, and so once you have an isoradial graph, you can naturally assign a rhombus graph, which will be important to define the model. So to define the rhombus graph, you take the original graph and you take all the circumcircles, circumcenters. So they're a specific embedding of the vertices of the dual graph. So there's a little lozenges drawn on the picture. And you join all of these to the vertices that are on the boundary of the corresponding face. Okay, and so when you do this procedure, it's quite easy to see that you get a quadrilateral graph in general. So you can do this for any planar graph taking its dual. But when moreover the graph is isoradially embedded, you have rhombi because all the edges that you have added are radii of circles, and they all have the same radii. So you have quadrilaterals with edges that have the same length, so you have rhombi. Okay, so here is a picture when removing the underlying graph where you really see that you have rhombi. And so with this, you can assign to every edge of your original graph here, you can assign to it a rhombus. And what will be important for us is this angle. So the angle theta e, to every edge e, you can assign an angle theta e, which is the angle of the rhombus at the vertex it has it common with the graph. Okay? And so the Ising model we will consider is when the coupling constants are chosen according to this angle. So the Ising model is said to be Z invariant and critical, so this is a definition due to Baxter, if the coupling constants are given by this explicit formula. So the coupling constant of the edge E is 1/2 of log 1 plus sinus theta E divided by cosine theta E, where theta E is the angle assigned to the edge. So where do these weights come from? So I'm not going to rederive them here, but I will tell you how Baxter constructs them. So first he assumes Z invariance. So this is a strong condition which says that the model is invariant under star triangle transformation of the underlying graph. So on isoradial graphs, you can naturally, if you have a triangle, you can naturally transform it in a three-legged star. And so asking that the model is invariant under such a transformation gives you a set of equations, and Baxter solved them, and what he gets is a one-parameter family of solutions, depending on a parameter k. And if on top of that you assume a generalized form of self-duality and uniqueness of the critical point, then the parameter is fixed to 0, and what you get is these weights. And so quite recently, Zhongyang Li and independently Hugo Duminil-Copin and David Simazzoni showed that actually the Ising model is indeed critical for these choice of weights. Okay, an example, when G is a graph Z2, then all the rhombus angles are equal to pi over 4, because all the rhombi are squares, so you have pi over 2, and the half angle is pi over 4. And when you plug this in these weights, what you get is 1/2 log 1 plus square root of 2, and you recover the coupling constants that were computed by Kramers and Vanier. Okay, so this is the critical Ising model we will be working with. Now, spanning trees is another very classical model of statistical mechanics. So again, you consider a graph, and on this graph you put configurations that are spanning trees. So a spanning tree is a connected subset of edges spanning vertices of the graph and containing no cycles. So here is an example of spanning tree on the graph. Removing the underlying lattice, you see it better. And so to make it a model of statistical mechanics, you put positive weights, you assign positive weight to edges, and the spanning tree Boltzmann measure is defined as follows. So the probability of a tree is proportional to the product over all edges in the tree of the weight of the edge, divided again by a normalizing constant, which is the partition function. And so we will be, in this talk, we'll be working with also specific spanning trees that were introduced by Kenyon and called critical. So you assume again that the graph is isoradial. So to every edge E, you assign an angle, and you choose the weight so that rho of an edge E is tangent theta E. Okay, so now I want to refer to the talk of Cédric Boutier towards the end of the week, because it was mysterious for quite a long time of why these weights were critical. Because if you see among all spanning trees, these do not have such a specific behavior. And so actually you can see also that you can introduce Z invariance for spanning forests, and then you also have a parameter K that comes into play, and for a specific choice of this parameter, you get this behavior, and indeed they're critical. You have a phase transition depending on the parameter K. So they are indeed critical in some sense. Okay, so but we'll be working at criticality. So the result I want to prove today is the following. So you take a critical Ising model on your graph G, so with these choice of weights, and you consider critical spanning trees on G bar, which is the graph G just extended along the boundary. Okay, so basically you have to think of G, but what you do, you add an edge for every vertex at the boundary. You add an edge exiting. This is G bar. But so the interior of the graph is also isoradial. And you put on edges the critical coupling constant, except at the boundary. So I'm not going to mention exactly what happens, but on the boundary edges you have to put specific specific weights, not coupling constants, specific weights. And so what I want to prove today is that actually the square of the partition function of the Ising model is equal to 2 times the number of vertices in the graph of the spanning tree partition function of G bar with the critical coupling constant. So this proves a relation between two classical models of statistical mechanics, where, I mean, now it's been, things have been occurring, but for a long time they were not believed to be related in any close way. And actually, yeah, the relation between the two is quite, is a bit distorted, but still it exists. And for the partition function, you have something which is a really simple relation between the two models. So what are the known results in this direction? So there are already results when the graph G is embedded in the torus, okay, instead of having a graph embedded in the plane. So in this case, the partition function is replaced by the characteristic polynomial. And so we have a proof of an equality up to a constant between the characteristic polynomials. Okay, so the first set of proofs were used using Fisher's correspondence, which is a correspondence between the Ising model and a dimer model on the Fisher graph. And so the first thing, we had an abstract proof of this fact in a paper with Cédric Boutillier. And then I provided a combinatorial proof of this relation, but which was, so using Fisher's correspondence, and which was quite complicated, actually. Then later on, David Simazzoni also proved this fact using Katz-Ward matrices, which is another classical approach to the Ising model, but it's also, it's not a combinatorial proof. It doesn't prove an explicit relation between the two. So the difference with the result today is first that on the torus, you have difficulty related to the homology of the torus, but you have no difficulty related to the boundary of the graph. And moreover, the construction I'm going to show is completely different in nature. It doesn't start from Fisher's correspondence, and it's actually much more simple. Okay, and so recently with Cédric Boutillier and Kylian Rachel, we also have now a proof of equality for characteristic polynomials for the torus. So it's an abstract proof, like in this paper, proving equality between the characteristic polynomial of Z-invariant Ising model away from criticality and Z-invariant spanning forests, which correspond to spanning trees away from criticality. Okay, so it really shows that this relation between the two models seems to be quite deep. It not only holds at criticality, but also away from criticality, where spanning trees become spanning forests, which can be rooted actually at any vertex. But for the moment, away from criticality, the combinatorics resist. And so also, it's nice to have equality between partition functions, but of course, our goal would be to have other observables, like spin correlations or that kind of stuff, to express spin correlations of an Ising model into spanning as an observable for spanning trees or spanning forests. But for the moment, also, we cannot do that. So the partition function is like the first step.
What is criticality for a spanning tree?
Okay, so Cédric will tell much more about it. His talk will be all about that, but basically, away from criticality, you can say the spanning forest, which can be rooted at any, it's like a killed random walk, so it can be killed at any, it is rooted at any vertex, okay? So this is away from criticality, and then when you get to criticality, the mass at every vertex gets to 0, so what you get is a spanning tree. Okay, so this is the phase transition that you have. Yeah, so you really have a correspondence between the phase transition in the Ising model and then the phase transition between spanning forest and spanning tree. Okay, but so Cédric's talk will be about really the study of spanning forest, Z-invariant spanning forest away from criticality. Okay, so now I will show you the proof of the result. So it's a combinatorial proof, and it consists of different steps. So here are the different steps. So what we start from the square partition function of the Ising model, and first we will use, so all these equality are up to constants, which are explicit. We will use that it's equal to the partition function of a dimer model, not on the Fisher graph, but on a bipartite graph. So I will just state the result, but not prove it, because it's a talk in itself, but that's the starting point. Then we will go from this partition function of this dimer model to the partition function of directed spanning trees on a graph constructed from this one. And then this step is easy. It's just going to dual spanning trees. So there's a bijection between spanning trees and spanning trees of the dual graph. So I'll say a quick word about this. And then from spanning trees of this graph, from these spanning trees, we will construct dimer configurations of the double graph. And then once you're there, just using Temperley and Fisher's, Temperley's bijection between dimer model and on the double and spanning trees allows to conclude. So it seems like there are a lot of steps, but honestly, I've been thinking about this for a long time, and I think it's a relatively direct proof of this fact. Also, a remark is that, of course, it doesn't provide a coupling. We're destructing everything at certain steps, so it's not it doesn't provide a coupling. Okay, so first the first step. So I will show you how to construct this bipartite graph from the original graph. So you start from the isoradial graph G, and then you take its dual. But it's real dual, so here I've put different vertices, but actually they're all glued together. So this dotted line means that they're all glued together. And then you do the rhombus graph, as I had shown before. So you do the joining all the vertices at the center to the boundary of the face. And also you do this at the boundary, so this vertex gets joined to these two, which are one and the same vertex. And so you consider this graph, and also you consider vertices at the crossing of the primal and the dual edge. And you take the dual of this graph, and that's the graph GQ. Okay, so it's easy to see that it's actually bipartite. So you have three different kinds of faces. You have square faces, which correspond to crossing of a primal and a dual edge. And then you have faces which correspond to vertices of the original graph. And then you have faces which correspond to vertices of the dual graph. So this is the graph GQ with the underlying structure removed. And so on this graph, we'll consider the dimer model. So the dimer model is another model of statistical mechanics. So introduced to represent the adsorption of diatomic molecules on the surface of a crystal. So a dimer configuration is also known as a perfect matching rather than coupling, perfect matching. So it's a subset of edges such that each vertex of the graph is incident to exactly one edge of the perfect matching. So here in red, you have an example of a perfect matching or dimer configuration. So it's quite rigid, so you cannot add any edge, because if you added, for example, an edge here, then this vertex would be incident to two edges, and that's not allowed. And if you remove any, for example, this edge, then this vertex would be incident to no edge, and that's also not allowed. Okay, so again, you put positive weight on the edges, and then you have a Diamond-Boltzmann measure, and the partition function is defined as the sum over all perfect matchings of the product of the weight of a configuration, which is the product over all edges in the configuration of the weight of the edge. And so the result that I'm going to use is that actually the square partition function of the Ising model is equal to this explicit constant to the dimer model partition function. So this result was, so there's a paper by Julien Dubeda proving this result using a sequence of mappings from the physics literature, so quite a long sequence of mappings. And also with Cédric, we provided another proof using another sequence of mappings, which has the advantage of providing a coupling with the XOR Ising model. So actually there are different proofs of this result. And also we worked for graphs embedded on surfaces of genus G. But anyway, so this holds, and I'm not going to tell you how it's proved, but you have, so working with the squared Ising partition function is the same as working with this partition function, and we understand quite well how one goes from this one to this one. Okay, so we're here, and so now we're going to go here. Okay, so to go a step further, I have to tell you how one computes the partition function of the dimer model. So this is a really classical result now and beautiful result by Castellane, and also proved by Temperley and Fisher, which dates back to the 60s. So the point is that the dimer partition function can be computed explicitly as the determinant of a matrix known as a Castellane matrix. So how is this theorem proved in two words? So consider a bipartite graph. It can be any graph. I'm stating it for GQ, but it can be any graph. So white and black vertices, edges, and then you have to have the same number of white and black vertices, otherwise you don't have perfect matchings. And suppose that edges of your graph are oriented. I will tell you how after. I mean, yeah, what you need from the orientation. But for the moment, just suppose that it's oriented. And you define the matrix K to be the adjacency matrix of your graph, weighted and oriented, meaning that lines are indexed by white vertices, columns by black ones, and so you have non-zero coefficients if and only if you have an edge between the white and the black vertex, the corresponding white and black vertex. And so non-zero, and the coefficient is the weight of the edge, that's why it's weighted. And then you have a sign coming from the orientation. So if W is oriented towards B, then you have a positive sign, and if W is oriented away from B, then you have a minus sign. Okay, and so if you write the determinant of this matrix and expand the determinant as a sum of her permutations, what you get is, of course, the signature of the permutation times a term which actually exactly correspond to dimer configuration. So because here you have matchings between black and white vertices, exactly perfect matching. So non-zero terms exactly correspond to perfect matchings of the graph. So you really have a candidate for your partition function. The only problem is the signature, because you would like to have all terms coming with the same sign. And this is where the orientation comes into play. So Castellane proved that you can construct an orientation of your graph such that the signs that you will get from coefficients of the matrix exactly cancel the sign of the permutation. Okay, and it's actually quite easy to construct. Which was really clever was to find it and prove that it exists. So for planar graphs, you can always do this. And so as a consequence, you have that if edges of your graph are oriented according to a Castellane orientation, then the dimer partition function is the absolute value of the determinant of K, because you might have a global minus sign coming out. Okay, so now we'll be interested in a slight modification of this. It's the following. So instead of assigning an orientation to edges of your graph, what you can do is instead you assign a phase. Okay, so you assign a modulus 1 complex number. So this notion of phasing assigned to edges is due to Kuperberg. And so instead, you define the matrix, so it's again your adjacency matrix. But what you add to the weight is actually the phase that you have assigned to the edge. Okay, and so when you expand it, you have the same thing, but now you have a global phase coming from the product of the different phases. Okay, and what Kuperberg has shown is that if you choose your phasing of the edges in an appropriate way, then you can have plus or minus 1 globally for every phase, and then you can also compensate the sign of the signature, and so you have the same theorem that holds. Now it's a modulus because you might have a global phase that comes out, but okay, so you can do the same thing with introducing phases, and this is what we'll be using. Okay, so how do we choose the phases for a graph? So so we want to compute the partition function of this graph GQ. So around every white vertex, you have actually 3 types of, they all have degree 3, and you have 3 types of black vertices. You have one which is corresponding to an edge which is parallel to an edge of the original primal graph. You have one which is parallel to the dual graph, and then you have these little legs that join the squares between them. Okay, and so the phase that we will use is one that has been used by Kenyon in his paper, well, in one of his papers. I'm not going to. Okay, and so it's the following. So you take 1 for all these edges, I cosine theta for these ones, and E I 3 pi over 2 minus theta E for the little legs, and then you have special boundary conditions. Okay, maybe something I haven't said, which was on the slide, but I didn't say, is that these are the weights when you do the mapping from the Ising model to the dimer model. For the dimer model, you get the weights sinus, cosine, and 1 through the mappings. Okay, this is in the correspondence. The weights come with it. So we have a dimer model with weights sinus, cosine, and 1, and so we're adding the phases. And it's a lemma that of Kenyon that this phasing is indeed flat, so that you can compute the partition function using these phases. Okay, and so what is important in the choice of these phases is that if you sum the 3, you have 0. Okay, not regarding what happens at the boundary because it's a special, but if you sum the 3, you have sinus plus I cosine, which is minus I, which is equal to minus I e to the minus I theta. Okay, so the sum of the three of those three terms is equal to 0, and this is what will allow us to go to the next step. So this is the remark, is that the sum of the three around a white vertex, the sum of the three contributions is equal to 0. So you can write any of the three. We've chosen the WB3, but you can choose any of the three. You can write it as minus the sum of the two other ones. And at the boundary, it's not really exact. You have a boundary contribution on top of it. And so with this remark, what you can do is, I'm not doing anything, but I'm just reinterpreting. So you can see your Castellane matrix actually as a Laplacian matrix, okay? So to see this, what you do is you identify, so the matrix K has lines indexed by white vertices and columns by black ones. So you do a matching, a perfect matching between white and black, meaning that you couple the W and the B3 at all times, and you replace it by a common vertex, okay? So it means that it's just changing the labeling. Instead of seeing it as W and B3, you see it, you just denote it by X, a common vertex. And seeing it like this, then your matrix, this becomes a diagonal term of your matrix, because this is KXX, and so it's minus the sum of the other two contributions, which correspond to oriented edges, contributions of an oriented edge of this oriented graph. Okay, so the Castellane matrix, you can actually see it as the Laplacian matrix of this graph, where the W and the B3 have all been merged together, and you have a natural orientation on this graph coming from the fact that you have white and black vertices. So it's actually exactly the full Laplacian matrix of this graph, with weights, with these weights on the oriented edges, from which you have removed a line and a column which correspond to what happens at the boundary. Okay, so with this picture you can, okay, so I said everything I wanted to say. So this Castellane matrix can be reinterpreted as this Laplacian matrix. And so once you have this, then the determinant of a Laplacian matrix is by Kirchhoff's matrix tree theorem is it's the sum of a spanning tree. So since our matrix is not symmetric, it's a sum of our oriented spanning trees of this directed graph GQ constructed from G by merging the white and the B3 and oriented the edges from white to black. Okay, so we've gone from the diamond model to this spanning tree model on this oriented graph. Okay, so this equality is just an explicit expression of it's just a Kirchhoff's matrix tree theorem, variant of a Kirchhoff's matrix tree theorem. Okay, so now we're here. So we're here. So now we go to the dual graph. Okay, so how does one go? So it's also a very classical fact that if you have a spanning tree of a planar graph, then the dual spanning tree is the dual configuration constructed in some ways also a spanning tree. So the dual configuration is defined as follows. So you take all edges dual to edges that are not in the graph. Said like this is complicated, but the picture is really easy. Okay, so but I will, before showing you a picture, I will show you, we're really interested in what is the dual of this graph. So this oriented graph, if you construct the dual, actually the point is that the dual of this one is the double. So the double is another graph that you can assign to an original graph, taking its dual as well. And it's nice to have it because by Tempelet's bijection, if you have dimers on this graph, then you have spanning trees of the original graph. Okay, so this is why we're glad to arrive at this graph. So I will tell you how the double is constructed, not if you're taking it as dual of this one, but just if you want to construct it from a graph. So you take your graph, and then you take the dual, And then you just put them on the same, you draw them on the same graph, and you add a vertex at the crossing of every primal and dual edge. So this is the double, okay? And so if you see, the dual of this one is exactly the double, except at the boundary, where actually I have added a black vertex, because here at the boundary it would not be, it would not correspond to the double of the G bar. So we have to extend it, but then you can do it, show that it doesn't change the partition function. So here is a picture of the bijection between spanning trees and dual ones. So if you have a spanning tree, on the dual graph, you take all the edges that were not present in the original spanning tree. Okay, so here it's in blue, it's the dual spanning tree. And so classical fact is that it provides a spanning tree as well, and so you have a bijection between the two. Okay, so instead of considering spanning trees of this graph, we'll consider spanning trees of the dual. And now we have to be careful, because we cannot just consider all spanning trees of the double, because they're spanning trees dual to oriented ones, which are specific. This graph is oriented, okay? So you don't have all spanning trees of the unoriented version of the graph. Some edges, they're oriented not in both directions, only in one. So you have a family of spanning trees of the undirected graph. So here also in the dual setting, you have a family of spanning trees of the double graph, and so we have to characterize them. So this is a dual spanning tree. So this is the object we're interested in. And so what we need to is to characterize the spanning trees of the double that occur as duals of spanning trees of the oriented graph. Okay, and so an easy lemma is that actually what happens is quite easy. It has to be a spanning tree, of course, and the restriction at every white vertex is one of the four following configurations. Okay, so for spanning trees in general of this graph, you could have degree 3 vertices, degree 1 vertices. What happens actually is that you only have degree 2 vertices and not all of them. Okay, and this is just seen by looking at the possible oriented versions that you have on the primal graph. So now we have a full characterization of the spanning trees that occur in the dual graph, and so we'll denote by C this condition. So we're interested in the set of spanning trees of the double that satisfy this condition, and we orient them towards the boundary towards the vertex of the boundary. Okay, so now we've been from there to there. So these are the spanning trees with the additional constraint. Okay, and now we want to go to the dimer model on this double. So from such a spanning tree of the oriented towards the boundary vertex, we will construct a dimer configuration. So how is it done? So the construction is actually, it's not complicated. So what you do is so you orient it towards the boundary, and what you do is you only take the edges that are exiting a black vertex. Okay, so from every black you have an edge exiting, so you only take this one. So we will not take the edge exiting from the white. So we're only taking half of the edges. Okay, so we're taking all the red edges. So this point resembles a little bit temporalist bijection, but the difference is that the spanning trees we have are more general than the ones of temporalist bijection. We have more spanning trees at this point than in temporalist bijection. So so naturally to every spanning tree you can assign a dimer configuration. So you have to prove that it's actually a dimer configuration, but that's not so difficult to prove. And so you can partition your set of spanning trees as a function of their underlying dimer configuration. To every spanning tree assign a dimer configuration. So this partitions your set. So it's actually disjoint. You have to see that it's a disjoint set. And that is because if you suppose that you have a spanning tree in two families, then it has to contain dimer edges of two different dimer configurations, but when you superimpose two dimer configurations, you must have a cycle if they're different, and so you cannot have a tree. Okay, so it's easy to see that these are actually disjoint. So as a consequence, you can write the dimer partition function as a sum over all perfect matchings of the graph of the weight of all the spanning trees in a given family. Okay, so we're nearly there. We have a sum over dimer configurations of the graph. What we need to be able to compute now is the weight of all spanning trees with a fixed dimer configuration. Okay, a priori it's a large family of spanning trees, and we have to control their weight as a whole. And so for this, we use the following proposition, which says the following. So if you fix a perfect matching, you're given a perfect matching of the double, then if you have an edge configuration which contains the edges of M and satisfy the condition C at every white vertex, then you know that it is a spanning tree. Okay? So you have it in one direction and you have it also in the reverse direction. So this is not immediate, okay? Because saying that to be a spanning tree, you must not contain cycles, for example, and this is not a local property, okay? So this proposition says that if you only fix half of the edges coming from the perfect matching and have a local constraint, so this is what will allow us to compute the weights. So half of the edges plus a local constraint guarantees that you actually have a spanning tree, so you don't have cycles, etc. Okay, and so this is what saves us and allows us to compute actually the weight of the family of spanning trees with a fixed dimer configuration, because you have the weight of the dimer edge, and then you have so you fix one of the edges around a white vertex is fixed by the dimer configuration, and then you know that you can have the other possibilities. Okay, always. So for example, if the dimer edge is this one, then you have two local possibilities, this one and this one. Not these ones because they don't have the dimer edge. So for every dimer edge, you know that actually you have two possibilities. And what is the contribution? So you have the edge of the dimer weight, which is what we want, and then you have the sum of the contributions of these two edges, but this is really simple because it's cosine plus I sine, or sine plus I cosine, whatever. So it's just an EI theta, and then all the EI theta factor, and so you can take them out, and so you can compute actually the weight of this whole family of trees just using the weight of the underlying dimer configuration, because the other local terms all get the same contribution, which factors out. Okay, so we've written the dimer partition function as a sum over all perfect matchings of the double times the weight. So the prime is only because it's essentially rho E. It's because there's the term EI theta on top, but essentially think that it's the weight rho E times a constant that you can take out. Okay, so this was the main last point. So we've been from spanning trees of this graph to this dimer configurations of this graph, and now I will show you quickly how temporally bijection goes. So it's quite classical, but nevertheless it's maybe useful to show it. So actually it's a generalized form of temporally bijection, which is due to Kenyon, Prop, and Wilson, which is an explicit bijection between dimer configurations of the double and pairs of primal and dual spanning trees, but if you have pairs, you have any of them, so that's enough. So how does it work? So you start from a spanning tree of a graph, and then you take its dual spanning tree, and then you root it at the boundary. Okay, you have to. So yeah, so you have to root them properly so that it works, and then. So you have this pair, and so as I said, one of my steps was reminiscent of temporally bijection. You take all the edges exiting from the black vertices, okay, again, and so you have these, you get half of the edges, and then you can easily prove that you have a dimer configuration. So the difference with the family of trees I had is that in the temporally bijection, you know that the edges are going to go straight. In my case, they could also go left or right. Okay, so this is why it's not, at that point before, it was not exactly a temporal release by ejection yet. Okay, so you go to dimer configuration, and conversely, if you have a dimer configuration, every time you have an edge, you prolong it, you go from the black to the white, and you prolong it one step, and then it will give you, you can prove that it will actually give you the spanning tree and the dual spanning tree. And so I think that I'm going to stop here. Sorry, I haven't taken my hour, but I guess it's okay. Thank you.
Questions?
In Ising FK, the crossing probabilities are given by square roots of harmonic measure.
Mm-hmm.
Is this related to here the Ising partition function being the square root of this? So the trees which already have to do with electric networks and random walks.
Yes,
so
of course.
Is it the same square root, or
it's certainly the same square root. So that's why I would like to. Yeah, it's probably that's why I think there's a strong relation, because the model which is more classically related to all harmonic stuff, it's spanning trees, I think. And so yeah, but for the moment I cannot. But yeah, this square root it comes from there, certainly. Yeah.
Do you have an idea of what's the analog of the spin for the tree?
No.
The observable? Or
Just the spin.
yeah. I mean
No, because you see, you lose. I mean, you
expect it or?
No, because even the contour representation, like the low temperature representation, you will not be able to map it. I mean, because it's like you do like high temperature expansion where you expand everything and then you resum. So I mean, at every step you can see what you do, and you see that you expand and then you resum in really different ways. So we will not. I really don't expect to be able to get something like a really simple representation between the two. The most I think we could get is maybe have a representation of correlations, but I don't know what one could expect.
Is there a way to understand what happens in your sequence of bijections when you compare what happens with two different graphs? I mean, one graph and you have one additional edge or one additional site, because that's sort of in the ratio of partition functions is well understood. So when you add one.
So you have a graph and then you just.
I mean, you let it grow, just to have a proof somehow by induction. I mean, because if you look at the partition function of the spanning trees, then you can view it as, the determinant, and therefore you have this natural hierarchical structure by letting it grow. So I was wondering whether there was a way to see what.
So follow really the track of adding one. Well, if you add an edge to
you add a site and.
Yeah, you add a site.
And then you have this double thing, and then you push something in, and then you wonder what happens inside before it comes out again.
Yeah, but you have to do it isoradially. Okay.
Yeah.
But you can do star triangle, for example. Then you add a vertex.
I don't know. Just
you have to do everything isoradially because otherwise everything breaks down. But so if you add a vertex, well, I'm not sure it's going to tell you that much, because at every step it just means adding a vertex, because the graphs are all constructed from the original one. So you just add this vertex all the time. But I'm not sure that you'll be able to say much more than, okay, it just adds everywhere. In the ratio, you mean? Do you see something occurring in the ratio?
I mean, because if you have the identity in the partition function, you can just show the identity in ratios when you add an additional thing, and then.
Yeah, I don't know.
Like to have a kind of an evolution of correlation functions or what?
Yeah. I don't know.
Just to ask the same kind of thing, is this only for simply connected domains, or you could do it also for
domains with holes?
Yeah.
I haven't thought about that. You have to be. One would have to check. Okay, the thing is, when you handle the boundary, there are some steps that you have to do to be able to handle it that I have a little bit put under the carpet. But so if you have two boundaries, I'm not sure that. Okay, it would be maybe have to be adapted, but not in a trivial way, because the boundary really plays a role. So if you have two boundaries, they're naturally rooted on. You will not have. I guess the object would be rooted either on one boundary or the other one, the spanning tree, and so then one has to be careful. So it's not immediate what would happen.
So you said you don't have a bijection, of course, but actually in most of the steps you showed you were actually using a bijection. So did I understand correctly that one of the main steps where you see this Castellane as a Laplacian?
This is an
That's why you
expansion.
lose track of the thing.
This, yeah, and already in the. Okay, so here it's not a bijection. Okay. Okay, and so once you're here, actually where you lose things. So yeah, when you do when you use the matrix tree theorem, actually you destruct everything.
Yeah.
Okay, because you take what the proof of the matrix tree is the diagonal terms which are really correspond to an edge in the diamond model. Then you expand them completely, and then you resum them to get spanning trees. So there you destruct everything. This is exactly the point. And then after, yeah, this is not bijection, but it's really it's really understood. And basically, yeah, it's nearly a bijection, but it's this point and then here. But you keep some information, the XOR information, so you don't lose everything either.
So that's where you use the matrix tree theorem is somehow.
Yeah, that's the point where you, yeah. And this is where, but this is also why I think you will not be able, because you really have to go to the spanning trees, because then it's near your bijection. So you really have the feeling that you cannot do anything else that at one point explode things and resum them in a really different way. But okay, I don't know.
Question? Okay, so let's thank again the speaker.